Hi, welcome to lecture 3, where we discuss arrays. And in this lecture, we will be discussing the memory arrays. Um, uh, the concept of arrays is basically refers to a repeated regular structure. Like, for example, when you have more or like a square type of shape, and you repeat certain patterns of cells. Of course, these arrays are necessary to implement dense design where you can pack lots of repeated cells. Very useful to create compact, low power, and hopefully fast designs. So it is important concept for arrays, and because arrays or memory are typically those repeated structures, we will be focusing on memory arrays. Okay, so just so you understand that the concept of array is this repeated structure, and memory use those arrays or repeated structures very commonly, and that's why we are focusing in this lecture in memory arrays. Memory arrays can be classified into three types: random access memory, serial access memory, and content addressable memory. Random access memory refers to those memories that accessing any item through read or write is not related to the item before or the item after. So you can basically access any word, any data in the memory. This is opposed to the serial access memory, which has certain sequentiality, certain order, where you can read or write to these structures. A random access memory can be classified as volatile or non-volatile. Volatile memory is this type of memory. When you unplug the power, you lose the data. Okay, so as opposed to what? Well, as opposed to non-volatile. So the non-volatile, when you save the data and you unplug the power supply, or you unplug it from the battery, the data is returned. Now, of course, they implement different type of technologies, and therefore we will address each in separate section. In this chapter, or in this lecture, we will focus on the volatile memory. So the volatile memory can be of two types: the static and dynamic. The difference between static and dynamic is the following. Static refers to or implements a feedback inverter in itself. It does not need a refreshment, versus the dynamic, where it implements the storage, not using a feedback, rather a simple capacitance. It stores the data on a capacitor. And we all know in these environment of small electronics that there is this leakage current, and so these capacitances leak the data. So we need to refresh the data frequently and periodically in this type of dynamic. So what's the use of dynamic? Well, it turned out these capacitances are tiny. So therefore, you can see that the static RAM, right, while it retains the data and it doesn't need refreshment and it is fast, the dynamic RAM is dense, meaning I can pack lots of information, but it suffers from data could be leaked, so you have to refresh the data quite commonly. Okay, and because of that, it is slow to be accessed. Now, the non-volatile memory, on the other hand, implements different technologies. In the earlier days, we had the mask RAM, meaning you create the mask RAM. I'm sorry, and RAM stands for read-only memory. The mask RAM, you create the transistor in a certain pattern where you implement the data. They are mass cram. They are more like implementing a truth table, to be honest, and that was the early application of it. Then we move to programmable RAM, where you can fuse those transistor that you need or you don't need. So to implement the truth tables or to implement the memory. Then, so this programmable happens once and you cannot erase it. Then we move to erasable programmable ROM, where you could erase the data using ultraviolet light, for example. But unfortunately, to do that, you have to remove the oops, remove the chip from the motherboard and put it and expose it to UV. It was a hassle. So then we moved to electrically erasable programmable RAM, and these are EEPROMs, and they were wonderful because you could electronically erase it and program it. You don't need to unplug the chip from the motherboard or expose it to any UV light. Everything is done electronically, the programming and the erasing. But unfortunately, these are bulky and large. So some folks in the flash memory came up with a scheme where you can make those EEPROM smaller by sharing the circuitries, the large circuitries, and reducing the size of the memory. So that's the flash RAM, basically what they have done. Now, so we have the first type, random access. Second time is the serial access. There is an order. We'll discuss the shift registers, the queues, okay. And the third type is the content addressable memory, and these are basically the memory that have the feature where you can search their content, and basically I can present a key, and I can search if this key exists in the data of the memory. Okay, so they're very useful for certain applications, and this is the third type that we will discuss in the next two lectures. So in this lecture, we'll continue with this introduction. Okay, and you can see, you can go through these notes that we have presented verbatim yourself. But here now we will start discussing the memory array architecture in general. So the memory array architecture in general, what you have here is that this is a memory, right? Typically we refer to these horizontal lines as words. Okay, so you have here a word. This is a word of 4 bits. Your textbook like to refer this as 2 to the power m, while in this example m is equals 2. So we have 2 to the 2, or 2 to the m of bits per word. Now this RAM has how many words? Well, this is word 0 all the way to word 15. So we have 2 to the m, I'm sorry, 2 to the n, 2 to the n. So this is here 2 to the n, 2 to the n words, where in this example, in this particular example, n equals 4. Okay, in this particular example, n equals 4. So 2 to the n, which is 16. And therefore, you can see easily that the size of the memory equals 2 to the n rows times 2 to the m, all right? And that gives you what? That gives you the size in terms of bits, okay? So in my example, 4 plus 2, that's equal to 2 to the 6, okay, which is equal 64 bits, all right. That can be stored in this memory. Again, look at the organization. Those horizontal refers to words, and those the vertical the words are vertically organized. So this is word 0, 1, 2, all the way to 15. Notice as well here in this organization that every we have these lines that are coming down. We call them bit lines because these are shareable bit lines. So this is This is bit 0, which is shared with all the words, and this is bit 1, and this is bit 2, and bit 3, shared between all the words. And obviously, whenever you have a shared resource in the hardware, you have to make sure that you don't have a case where two words are accessing this shared resource. So only single word access the bit line. And at the top here, we have bit conditioning, this bit conditioning, and this is typically a pre-charged circuitry, etc. And then I have column circuitry, which is basically drives the output to the outside. Notice that here I have 2 to the m bits. Now, there is an interesting theory here is that, that this is a tall structure. In fact, we don't do memory arrays like so, because in this example, we have the size or the number of words of the memory is 16. In reality, we know it's not the case. Memories are much larger in terms of number of words. So if we want to organize these words in this vertical fashion, then we will have a very tall, skinny memory arrays, and this leads us to folding. In practice, what we do, we fold. In other words, we kind of fold it like a piece of paper, this memory, so that we can have more than one word at the output. So in this case, you can see that here, this output represents just one word. When we fold the memory, we will see that we can have in these column circuitry, you have to choose between two words in the output. So we will refer to the folding with a parameter. We call it K. In this case, in this architecture, we are not doing any folding because we have one row per word. Okay, one word, one row per word. So this row represent a word, a word, a word, a word, a word. But when once we start folding, we will see that one row represents more than one word, and the column circuitry has to choose the correct word. So before I leave this slide, understand the parameters of this array. We have n, which is the number of words. We have m, which represent the size of the word. So 2 to the n, a number of words, 2 to the m, the data size, and k represent the folding. Also, we need to understand here something interesting here, which is this decoder, and this decoder really activates one horizontal line. In this case, the horizontal represent one word. In the next slide, we will see that this horizontal line represent more than one word. So it activates one horizontal line. So here, because we are activating 1 out of 60, in this case, n equals, in my example, 4. Also, we will see very shortly that we will have a multiplexer in this circuit, which is the column circuitry. Again, let me summarize what I just said in terms of this memory array. You have, first of all, you have the array itself. So let me choose a different color here. Okay. You have the array itself, that's one part. You have the decoder, okay. You have the bit line conditioning, and you have the column circuitry, okay. And you have to understand how these parameters play in this picture here, especially this folding k factor. Okay, all right. So we don't want tall and skinny memories. So what do? We fold them. Okay, let's talk about folding now. In this case, what we did, we fold the memory into where every row here, every row represent two words. Okay, every row here represent two words. And now for that to happen, what we do is that we have in this column circuitry, we have to choose one of the two words. You can see that here in this column circuitry, there is a multiplexing happening. Okay, so I have to choose for in the bit 0 of the output, I have to choose one of two bits, and bit 1 in the output, I have to choose one of the two bits, and bit 2, one of the two bits, bit 3, one of the two bits. And therefore, you see that here I have what I call column decoder, which receives k bits. And k indicates for me the folding factor. Since I fold this once, k equals 1. So this k bit, which is part of the address, okay, of the memory. I forgot to mention in the earlier slide here that this address here size is equal in bits. Okay, the address size. So since I have 16 words, so n here equals 4. Okay, now let's go back to this slide here. So the address here in my example, n equals 4. Now and since I fold and I am using one bit here, k is the folding, I'm using one bit to select one of the two words for the column circuitry. So I used one of the address bit. How many remains in terms of address bit? N minus k. In my example, 4 minus 1, that is equal 3 bits. So you can see that this decoder here decodes 3 by 8. So it will activate one of these rows, and every row of those contains two words. So it contains two words which will be selected by the k bit at the bottom here. And the rest are the same. You have the bit line conditioning, you have the column circuitry, okay, where you choose one of the two words based on the k bit. Now let's see the size of this array. Supposedly it shouldn't change, but let's double check it. You see, in terms of the height here, the size of this is 2 to the n minus k, right? Now, in terms of the width here, in terms of the width, it is 2 to the m plus k. Okay, so now let's compute the size now. So the size equal 2 to the n minus k multiplied by 2 to the m plus k, which is equal to 2 to the n plus m, which is 2 to the, in my example, 2 to the 6, which is 64 bits, and the size didn't change. So the size does not change. What I have just changed is the organization of the array. I need this array a square, and this is very desirable in array structure. It is desirable to have a square or close to square structure as opposed to tall and skinny. Okay, so this is the structure. Now the question is, how do I choose this k factor? And the answer is, this k is chosen so that you will have as close to a square structure as possible, given different values of n and m. Okay. Now, um, of course, here in these cells can be SRAM or DRAM cells. In this case, we will study SRAM cells. The SRAM cells are known that they are smaller than flip-flops, but they are and faster than and larger than DRAM. So they are smaller than flip-flops, but they are faster and larger than DRAMs. So typically they are used to implement fast memories like caches, register files, tables, buffers, those SRAM structures. And S stands for static. Okay, so that's one of the implementation that we can use for SRAM is just a simple feedback latch here, which is shown right here. So this structure is just one cell in my diagram, the previous diagram. And you can see this structure has this bit which carries the read and write data. It's the same bit. And I have a control line which says write and a control line which says read. Okay, and you can see that of course you have the control write and write prime and read prime, of course. Now you can see that here I have this transmission gate here, this transmission gate, which allows me to access allows the data to access this cell to write the data. Now, this is if this write and write prime are asserted or activated so that I can open up this transmission gate. Now, if write equals 0, we do not write to the cell. Now, the read operation occurs when I enable this try state, and this is by activating the read and read prime. And you can see that I can read the data and send it to the bit line. It is important that this condition write and read signal are not one at the same time, because if they are one at the same time, you will have a collision on this shared bit, because this here, uh, this here, this is a shared resource, which is the bit line. So if you are writing to it and reading from it, there will be a clash, because if you are writing here and you at the same time you are driving the data, because the data that is being written is driven from other circuitry, and at the same time you're trying to read the data onto the same physical wire, then you will have a collision. So this condition should never occur, okay? Because it whoops sorry should never occur, because it will cause a collision. Okay, all right. This circuit, unfortunately, is bulky. It has 12 transistor. We don't use it. It's large. Nobody uses this. So what we need to reduce the size of the cells and make them small as possible. Okay, now one small cell that people use 60 as opposed to the 12T we saw earlier, and the 60 is very simple. Do not be intimidated with this circuit, because all what it is, you have a back-to-back inverters, okay, back-to-back inverters, and you have access transistors. That's what's into it. But the trick is the sizing of these two inverters. That's what we will spend the time on it. The sizing of these two inverters. Okay, so you have these are the back-to-back inverters, the back-to-back inverters right here. Okay, and then you have access transistors activated by the word line, which comes from the decoder, and then you have the access transistors are connected to bit and bit bar lines. Okay, so let's see, review the structure again. So you have the back-to-back inverter, you have the word line, okay, which activate the access transistors, okay, the word line and access transistor. Look how the connectivity, and then you have the bit and the bit line connectivity. So these are important structures for these. So how can I do the read and the write operation to such structure? So let's see how we can do the read. In terms of the read operation, so what we do is the following. Let's take an example here, and we'll follow on the. Suppose, for instance, that I have on this node a 0 stored, and this node a 1, and we'll say that we are storing a 0 in this bit in this cell. And suppose, for instance, that I want to read this, meaning I want to read the 0 value into this line here, okay? And I want to read the 1 value into this line, into the bit lines, because this bit and bit bar, it's what transmits the information from the cell to the outside of the cell. Okay, so the first thing I do, step number 1, is to pre-charge both lines high. So this is being pre-charged to VDD and pre-charged to VDD, or close to VDD. Okay, these two lines. Now, who does that? It's the bit conditioning circuits, which we discussed earlier in the array structure. Then what we do, we turn on the word line. So this is step 2. We turn on the word. So this was not active, then it becomes active. So the word line is 1. Now understand that we turn on the word line if we are accessing this word particularly, meaning other words that are not accessed the word line will be a 0. So we only activate the word line of the word that we are accessing. Now, so then what we do in this case, notice that here, once we activate this, so this is on and this is on. This transistor is on, both A1 and A2. Now, once they are on, notice that for this transistor here, let's use a color here. For this transistor, we have here VDD, right? And also we have at this node I have VDD. So there is no action really. There is really no action for this node. So this is here VDD, and so across this transistor there is no action. Oh, the action is here, right here, because at this node I am pre-charging VDD, and at this node there is what? There is 0 volt. Okay, so what happens? I will start to discharge this bit line through A1 through D0 to ground. And this is shown, you see this bit here, this is shown in this diagram. You can see this. Once I turn on the word line, you can see that the bit line is going down, 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 because it's being discharged. And now at the end, you will see that this VDD becomes 0 volt, which corresponds to the data that it's stored in the cell. The bit stays high, the bit bar stays high, and the bit is discharged to 0 volt. And that's what I want. I want to reflect the values that are stored in the cell onto the bit lines, and that's what is a read operation is all about. Notice there is a little risk here because there's a bump here on the Q node. This is a Q node, very critical, and this Q node. Oops, sorry. Uh, this node here, Q, is reflected at this bump here, this bump here. So because I'm discharging here, this node goes up slightly and then discharges now. So this is because of the charge sharing that is happening between the bit line and the Q node. But it is critical that this discharging inverter, I'm sorry, discharging transistor, MOS transistor, is strong enough. And that's why we say, D1 must be much, much stronger than A1. D1, which is the discharging MOS transistor, much stronger than the A1, which is the access. How do we make this? Well, it's all about WL, for D1 should be much larger than WL for A1. That's how we make transistors stronger, by varying the sizes of WLs. Okay, so this is the read operation where I copy the value of the cells onto the bit lines. How about the write operation? In the write operation, what I do, I want to force the values that are in the bits, right, to into the cell itself. Okay, so let's see how we do that. Okay, so in this case, what we'll do, suppose I have a value here. Let's use a red color here. I have Q equals 0 initially, all right, and Q bar is VDD 1, which is VDD here, all right, and suppose I want to change their values. I want to write a 1 on Q and a 0 on Q bar. So what do? I pre-charge the bit line, drive the bit line high, and so I pre-charge this to VDD. All right, because this is what I want to write 1 into Q, and the bit bar to discharge it to 0 volt. Okay, and now then I turn on the word line. So I do the pre-charging while word lines are off, and then I turn on the word lines. Okay, what's going to happen here? Well, interesting enough, what's going to happen, notice here that there is a 0 volt here, and there is a VDD here. Now, what happens is that this Q here, this Q, what it will do, this node here, this node is being charged by whom? By this transistor, because this transistor is on. So he is the P2 is charging this node VDD, supplying the current to to Q underscore B with the currents to keep it high. And at the same time, when I turn on the A2 axis, the A2 is trying to discharge this node to zero. Now, eventually, what I want to discharge Q bar to zero. So it is important that this A2 is much stronger. Oops. Is much stronger than P2. If A2 is stronger than P, what happens? You will see that this node will start discharging, and it will discharge down, 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 down. Notice that here this node, what it's doing, it is activating D1, right, when it is VDD, and deactivating P1. But when I start bringing this node, which is Q bar, to zero, then what happens? I will activate P1 and deactivate D1, and that will start charging this node, which is Q, to VDD. Okay, so you can see this Q here node, it is coming, it's going up and up and up. And why? Because I'm turning off D1 and I'm turning on P1. But the initial action happens in this side, all right? And the initial action happens in this side where it is important that what triggered this cycle is that P2 is much less than A2. A2 is very powerful, so we start discharging first, and that's why we have this condition over here for the right operation. So eventually, what I have is that I have the 0 volt copied in the Q bar, and I have the VDD copied into the Q, and then this becomes VDD, and that is essentially what's the right operation, which is to copy the voltages on that are pre-charged or pre-discharged on the bit and bit bar onto the inside of the cell. Now, it is important that my SRAM is a stable circuit. And to sum up what we discussed, we said for the read operation, it is important that those transistors, right, the NMOS, are stronger, right, are stronger than those access transistors. Okay, that's for sure. And then what we said, it is important. Oops. That's not what I want to do. And then what we said, it is important for the right operation that the access transistors are more powerful than the P transistors. So to sum up all of that, to have read stability and writability to the circuit, I will to be able to have stable operation and access. Those NMOS of the inverters should be the strongest. Those PMOSs should be the weakest, and those access transistors should be of intermediate strength. Again, let's be very clear. When we say strong or weak, okay, or weak, you're talking about the W over L of the transistor. That's what determines a strong or weak transistor. Okay. All right. Now, finally, here we talk about the noise margin here, and basically we try to ask ourselves the question: what type of a noise if I inject to this circuit, which is my SRAM circuit, then I will write erroneously the data. And what we do to start with, we try to plot the transfer characteristic curve, and basically I'm plotting here V2 versus V1, and we are familiar with this curve here because it's an inverter, and because V2 is an inversion of V1, V1 is inversion of V2, we end up with this type of curve. Now, to compute the noise margin, once we plot the characteristic curve, what we do, we try to draw the largest square here in these envelopes, okay, and the side of the square, the side of it is the noise margin. So for this cell, if my noise is less than 0.32 volt, then I am safe. Otherwise, if the noise increases, I will risk flipping the data to an opposite polarity erroneously. So for instance, in this circuit, if I have inject a noise of zero point 0.4 volt, then I risk to move the data from 0 to 1 or 1 to 0, the stored information from 0 to 1 to 1 to 0 erroneously. Well, of course, what happens if I inject less than that? What if I inject a noise of zero point 0.2 volt? Well, the circuit has a recovery mechanism that it will recover very nicely. This type of structure has a parallel in physics, by the way. In this mechanical system. So as I can have, for example, suppose I have this mechanical system where I oops, sorry, it's not. Um, let's say, for example, I have here um, something like this. Uh, okay. And suppose in this system I have a ball here, and notice I have 2 points, point A and point B. If I have the ball here, the ball is in a stable position, right? And if even if I move the ball over here, it will be in a stable position. But if I place the ball here, right, it's not stable. Any noise will flip it to either this side or this side. Okay, so now what if the ball in this physical system is situated here? If I push the ball all the way here, the ball come down, and but if I push the ball in with a force that brings it all the way to the top here and flip down, then I have injected a noise that will destroy the saved data. I have injected a force on this ball that it will not bring it back to its stable position, rather it will take it to the wrong position. So while A and B are stable position, like the 0 and the 1 here, these are stable positions. The noise can be of such force that it will overpower the stability of the circuit. Okay, now with that, I conclude this section, and the rest of this chapter is reading material. We conclude arrays in the next part of this lecture. Thank you very much.